mana.
Good evening to all. Am I audible? Can you message me in the chat box? If I'm audible, just mention in the chat box.
Hello, English learners. Lesson is dismissed.
Am I audible?
Hello, English learners. Lesson is dismissed. In versus into.
Okay. So, okay, I will start the class. So today we will discuss permanent magnet moving coil. Permanent magnet moving coil is a measuring instrument. So we call it as, in short form, you can call it as PMMC meter. Okay, PMMC meter. You can call the permanent magnet moving coil as P. Sorry, this cursor is very sensitive. 1 second. Okay, you can call it as PMMC meter. meter or okay, so you can call it as PMMC meter, which is a measuring instrument. You can even call this permanent magnet moving coil meter as this galvanometer, okay, or de-Arsenault meter, okay. So permanent magnet moving coil measuring instrument can be called as galvanometer or de-Arsenault meter, okay. So either you call it as galvanometer or de-Arsenault meter or permanent magnet moving coil, all three are same, okay. So the purpose of this permanent magnet moving coil meter or measuring instrument is to measure the current through the coil when by the coil's angular deflections, okay. So if there is a coil, and if there is angular deflection in that coil, then we can measure the current flowing through that particular coil by using this permanent magnet moving coil instrument, okay. So this permanent magnet moving coil is a conductor that is placed between two magnetic fields, okay. So it is a conductor which is placed between two magnetic fields to create a stationary magnetic field. So in this permanent magnet moving coil instrument, there will be a conductor which is placed between two stationary magnets, okay. So here, since the magnets are stationary, since the magnets which are used here are stationary, okay, and which are the which are not the electromagnets. Electromagnet means we will take a ferromagnetic material, we will wound a coil around it, okay. A ferromagnetic material is taken, a coil is wounded, and current is allowed to flow through that. Some current is allowed to flow through that coil, so that ferromagnetic material will start to act as a permanent, acts as a electromagnet. So instead of using electromagnets, here we are going to use permanent magnets. That's why it is named as permanent magnet moving coil instrument, okay. So here magnets are stationary. The permanent magnets which are used here are stationary. They are not moving. The coil will be moving, okay. So these permanent magnets, as they are stationary, they will definitely create a stationary magnetic field, okay. Since the permanent magnets are stationary, they are not moving, they will create a stationary magnetic field, okay, because of which coil will move. Coil is moving when we know when current carrying conductor is placed in the magnetic field, it will experience a force which is the principle of a motor. That's what happens here in this permanent magnet moving coil instrument, okay. So when the coil is placed in the this is a permanent magnet moving coil instrument, okay. So here if you see, there are few more images with me. So here if you see, this is our magnet, okay. So this is the north pole, this is the south pole of the magnet, and this is the coil which is in rectangular shape. It's black color what you can see here. This is our coil, it is in rectangular shape. So see, this is rectangular shape. So coil is placed in between these two north pole and south pole. So since this magnets north pole and south pole, they are not moving, definitely if you see these straight lines, these lines, okay, they are the magnetic flux lines. So this, okay, so these magnetic flux lines are nothing but our magnetic field. So magnetic field will also be stationary here. So here when this coil is placed in this magnetic field, what will happen is it will experience a force, or we can say it will experience a torque, okay, because of which this coil will start to move in between these two permanent magnets, okay. So these are the this permanent magnet moving coil instrument. Its working principle, basic principle we can say, is called as de Orzaval principle. Okay, it works on the principle of de Orzaval principle. Simple, in simple words, if you want to know how it works, means it works on the motor principle. Motor working principle is similar as the working principle of this permanent magnet moving coil instrument. Okay, so let us see how it works. So you can see here in this image, a north pole is there. This is our north pole. Okay, so and if you see here on the right side, there is a south pole, north pole and south pole. Okay, I couldn't write S properly. North pole and this is south pole. I'm unable to write S. Okay, this is S. This is north pole. So in between north pole and south pole, okay, magnetic flux lines are there. Okay, magnetic flux lines are there. Okay, as I have already told you, the working principle of this permanent magnet moving coil is based on the motoring principle. Okay, so whatever motor principle is the working principle of the motor is the same principle is applicable here. So when a current carrying coil is placed, so here if you see here, this rectangular, this rectangular portion, what you can see, I will erase the ink and just observe this portion, this rectangular portion. Here it is written C, isn't it? So that is our coil here. What we are seeing here is the upper view. That's why it is not looking like a coil. It is looking like a rectangle, but it is the coil. So when a current carrying coil is placed in the magnetic field, okay, what will happen is this coil will experience a force and this coil will start to move. Okay, so but here usually this coil is attached to a spindle somewhere, you can see. Yeah, so if you see here in this image, you see here, this is our north pole, this is south pole. Okay, north pole and south pole. This is, you can see, this is a rod here, and around this thin rod there is an iron core. You can see iron core. This is cylindrical structure. You can see here a cylindrical structure is there. This cylinder, this is our iron core. Okay, and around this iron core a coil is wounded. If you carefully observe this black color portion, if you see, this is our coil. Okay, this is our coil. This is rectangular in shape. Okay, so here we can't see the other side. So this coil is rectangular in shape. Okay, and to this rod another portion that is wounded here, that is a spring is wounded here to provide the controlled torque. Okay, to provide control torque, a spring is wounded here. Okay, so this coil, so here north pole is there, here south pole is there, so definitely what will be there in between, there will be magnetic field. When this coil, current carrying coil, this is this black color strip, like so you can see a thin strip here. So what you can see here, that is our coil. So that coil, when it is placed in this magnetic field, current carrying coil, when it is placed in this magnetic field, what will happen? It will experience a force, and force means we can say it will experience torque. Okay, because of that torque, what will happen? This coil will start to move. Okay, okay, this coil will start to move. So I have few more images. Let me show you. See here, this is the upper view. This is yellow color portion is the coil, north pole and south pole. Okay. So this movement of the coil, you can call it as de Orson-Wall movement. This movement is known as de Orson-Wall movement. And this thin rod-like structure, this supporting structure, thin rod, it is to that rod a pointer is connected. Okay, so you call that pointer. This black thin line is this one. This is the pointer. You can call it as light indicator. Okay, so this light indicator is pointed towards the reading scale here. Okay, and below that there will be a mirror also. Okay, so now let us see different parts of this permanent magnet moving coil instrument. So if you see here, there is an external shield. So I got some image from the internet. This is the image. So this is one. This is the external shield, this portion. This is the external shield. Second one is permanent magnet. Okay, 2 is the permanent magnet. You can see 2 is here. So this is our permanent magnet. Okay, and I will just erase the inks. Okay, next to 3. 3 is the moving coil. So where is 3? This is 3. See here? Here, this portion, if you carefully observe, this is the moving coil portion. Okay. Next 4. 4 is the control spring. Okay, 4 is the control spring. So if you carefully observe, it is the spring. This is the spring. Okay, this is the spring. 4 is the control spring. What is 5? 5 is the pointer. Okay, so this is it. This is the pointer. Okay, 5 is the pointer. Next, 6. 6 is the arrangement of zero balancing of the pointer. So initially pointer should be at the 0 position. So this is 6. So this is 6. So this is the arrangement which is provided, because of which initially the pointer will be at 0 position. Pointer will be at 0 position means initially we already know this is our 0 position. So initially the pointer should be held at 0 position. Okay, when you look at a meter, we can see 0 position. Initially pointers in the meters will be at 0 position. Okay, so the pointer is held at 0 position with the help of this 0 arrangement. Okay. Okay, so this arrangement for 0 balance, this is some U-shaped structure is provided. Okay, so if you want, I have few more images. See here. So this is our pointer. This is the scale. This is North Pole. This is South Pole. This is the spring. Okay, so this is our iron core. And this black color lines, if you observe carefully, this rectangular shape, the thin black color lines, they are the moving coils. Okay, so here to provide control torque. Okay, so control torque. So upper spring and lower spring, 2 springs are provided in this image. So to means I have few more images. So see this one, this black color line, that is our pointer. Okay, this is our pointer. Next image, mirror. So there will be a to take the reading accurately, we need a mirror. So this portion, this is below the scale. Okay, this silver colored portion below the scale, that is the mirror. So in the laboratories, when you look at the meters, you can see the mirror. Okay, so next time when you go to the laboratory, you just look at the meters, you can see the mirror. So moving coil, where is my cursor? This moving coil, where is the moving coil? This orange color portion, you can see, this is our moving coil, orange color, that is a moving coil. Okay, next, spring. So see here, you can clearly see the spring, this silver colored coil, you can see. So it's looking like a coil, isn't it? That is the spring. Okay, next, dial. This is the dial. Okay, and these are the permanent magnets. Okay, North Pole and South Pole. Okay, so this iron core is there. You can see here this steel. See, it is very shiny here. So this is the iron core. So iron core, it can be spherical. Okay, if iron core is spherical, the moving coil will be circular. Okay, so and if the iron core is cylindrical, so if you observe here, this is cylindrical in shape, isn't it? Iron core, if you see in the other images, this is our iron core. You can see it is cylindrical in nature. Since the iron core is cylindrical, the coil is rectangular. Coil means what? Moving coil. So this black color portion. Okay, so you to be see here, this is the coil. You can see it is rectangular. Iron core is cylindrical. So moving coil will be rectangular. So due to this iron core, the deflecting torque that will increase and increasing the sensitivity of the instruments. Okay, so here we since we are using cylindrical type iron core, what will happen is the deflection torque will increase. Okay, as the coil moves, and this increases the sensitivity of the instrument. Okay, and now unnecessarily this moving coil should not move, isn't it? It should, okay, and if coil moves, this handle, we can call this as a support or handle, it will move. If it moves, pointer will move. Okay, this pointer will move. So initially, as I've already told you, the pointer should be at zero position. Okay, and unnecessarily the pointer should not move. So in order to provide controlled torque, the springs are provided, upper spring and lower spring, they are provided to provide the controlled torque. Okay, so these springs, they are made up of phosphor bronze. Okay, so so now when the current carrying coil is kept in the magnetic field, what will happen? The coil will move. As the coil moves, moving coil. Okay, so this moving coil moves. When the moving coil is moved, what will happen? The pointer will also start to move. Okay, so this pointer will move over the graded scale. Okay, so this pointer is usually lighter in weight. This pointer, it is usually lighter. I will erase all inks. Okay, this pointer, it will be usually lighter in weight. Lighter in weight so that it can deflect rapidly. Okay, so if it is heavy, it is not easy to provide proper deflection because of its weight. So it is its weight is light so that it can deflect rapidly. And as I have already told you, there will be a mirror. It is not shown in this image, but you can see in this image there is a it is shown, mirror is shown. So there will be a mirror below this grading scale. Okay, so the purpose of the mirror is to whoever is taking the readings, they will be able to take the readings accurately. Okay, without any parallax error. So in order to avoid parallax errors, okay, mirror is placed. Okay, so so the scale markings, see here you can see the scaling. That is it. This is the scaling of this permanent magnet moving coil. The scale markings of this permanent magnet moving coil instruments are usually linearly spaced. Okay, if you observe here in this image, it is also linear. So linear spaced as the deflection torque of deflecting torque, and hence the pointer deflection is directly proportional to the current passing through the coil. Okay, so since the deflection torque and the pointer deflection both are directly proportional to the current passing through the coil, therefore the scaling is linear for this permanent magnet moving coil instrument. Okay, so this is about permanent magnet moving coil instrument. So let us go to the another instrument now. Let us go to the next instrument, moving iron instrument. So moving iron instrument, you can even call it as MI instrument, moving iron or MI instrument. So this instrument, which is known as moving iron instrument, it is used to measure the flow of current or voltage. So MI type instruments are used to measure current or voltage. You can see here in this image, here you can see A. That means this is an current measuring instrument. Okay, so these are usually used to measure either Usually in the laboratories, they are used to measure only AC currents, but mostly you can even use these instruments to measure AC or DC currents. Okay, so this is the internal diagram of this moving iron instrument. Okay, so this instrument is very popular, and it is used, as I have already told you, to measure both AC as well as DC currents. And if you see the scaling of this instrument, if you see here in this image, the scaling will be non-uniform for the moving iron instruments. So just observe the scaling: 0 to 5, 5 to 10, 10 to 15, and 15 to 20. If you observe, the scaling will be non-uniform for moving iron instruments. Okay, so and this moving iron instrument, it usually consists of a moving iron. Okay, consists of a moving iron that moves in response to the magnetic field generated by the current flowing through a coil. So there will be a coil. So you can see it is mentioned here, coil winding. Okay, so there will be a coil here. So corresponding to the current flowing through the coil, okay, depending on how much current is flowing through the coil, the moving iron will move. So there will be iron piece inside this moving iron instrument. Okay, that iron piece will move according to the current flowing through the coil that is inside this instrument. Okay, so in this MI instrument, there will be electromagnetic interaction between current carrying conductor and moving iron. Conductor means coil. Okay, and here electrical energy is converted into mechanical movement of the pointer. So here in the coil, current will be flowing. Okay, okay, so that energy is converted into mechanical energy. Mechanical energy means here when current flows through this coil, pointer will automatically start to move. Okay, and this pointer will move, and we can measure either current or voltage. So here the core component is the moving iron. In this instrument, in moving iron instrument, the core component, the main component that is performing the main role is the moving iron. Okay, it is this moving iron. It is either placed inside the coil. Okay, it is either placed inside the coil near or nearby to the coil. So here in this image, it is placed nearby to this. These are, you can see, small rounded structures here. They are all the coils. So it is either placed inside the coil or nearby to the coil. Okay, so when current flows through the coil, it creates a magnetic field. That magnetic field interact with the iron piece, and it will cause the iron piece to move. Okay, and this movement of the iron piece will be transferred to the, this movement of this iron piece will be transferred to the movement of the pointer, because pointer is attached to the same handle to which this moving iron is attached. Okay, and as the pointer moves, automatically we can, so to whatever position the pointer moves, we can measure either the current or voltage of the of that particular measuring device, whether it's a current measuring MI instrument or voltage measuring MI instrument. Okay, so here damping system is also provided. Okay, so similar to your permanent magnet moving coil control spring, here also damping system, counter weights are also provided. Here you can see balancing weight. So damping system is also provided to stabilize the pointer quickly without any oscillations. Okay, in order to avoid any oscillations, damping system is also provided. Okay, so when an electrical current passes through the coil, as I've already told you, what will happen? Uh, Magnetic field is induced, and this field will create a force. Okay, because of which iron piece will move. Okay, so when the iron piece moves, the movement of this iron piece, it is proportional to the square of the current flowing through the coil. Okay, so the movement of this iron piece will be proportional to what? Square of the current flowing through the coil. Okay, and with how much force this moving iron this moving iron will move. Okay, this moving iron will move. It will depend on, okay, how much current is flowing through the coil. Okay, so depending on how much current flows through the coil, the movement of the iron piece will vary. Okay, so, and this movement is mechanically linked to the pointer. Okay, as the iron piece moves, since this mechanically connect pointer is mechanically connected to this moving iron, therefore as the moving iron moves, automatically the pointer will also move. Okay, and the force or the torque that is induced here in the moving iron, it will depend on what? Square of the current flowing through the coil. Okay, so these moving iron instruments, they are used to measure both AC as well as DC currents. So this is about moving iron instrument. Let us go to the next instrument, that is Wheatstone bridge. Our next instrument is Wheatstone bridge. I think this Wheatstone bridge is most familiar instrument to you. So this is our Wheatstone bridge. This is it. This is our Wheatstone bridge. Yeah. So this is what is available in the laboratories. You can see a galvanometer here. Okay, and you can see series resistors, unknown resistances. Here you can, I'm sorry, these are the series resistances. Here you can connect an unknown resistance, and here you can connect external battery. Okay, and, so let us see how this Wheatstone, what is the how this Wheatstone bridge operates. Okay, this Wheatstone bridge, you can even call it as resistance bridge. Okay, Wheatstone bridge is also known as resistance bridge. Okay, so the purpose of Wheatstone bridge is what? To determine the unknown resistance by balancing two legs of the bridge circuit. So where is the bridge circuit? This is our bridge circuit. Okay, so here Wheatstone bridge, you can see it has four arms. Okay, it has four arms. So by balancing the two legs of the bridge circuit, total four arms means, or four legs we can say. So total four legs are there in this. Okay, so total four legs are there. Net, am I audible or not? Am I audible? Am I audible? Can anyone inform? Mention in the chat box. Am I audible? Okay then. Okay, I will continue. This is the last topic. As soon as this topic is over, I will conclude today's session. And if possible, tomorrow I will conduct one more online class of some other topic. Okay, so if I'm going to take online class tomorrow, I will mention it. I will just inform people. Okay, so today's session is only on measuring instruments, so I don't want to include any other topic in this. So that's why, okay, even though I may not, it may not take more than, I think I will conclude within 10 to 15 minutes. Okay then. So, so this Wheatstone bridge is what? It's a low resistance. calculating bridge. Means we can determine low resistances using this Wheatstone bridge. You can even call this Wheatstone bridge as a resistance bridge. Okay, the purpose of this bridge is what? To determine unknown resistance by balancing two arms of the bridge circuit, or two arms, or you can even call it as two legs of the bridge circuit. Okay, so one of the arm consists of unknown resistance here. So here you can see this here. This R is our unknown resistance. Okay, so S is the variable resistance. P and Q are the fixed resistors. Okay, so Mr. Samuel Hunter Christine invented this Wheatstone bridge in 1833. Um, and in 1844, some Charlie Wheatstone, he popularized it. Okay, so he made some improvements and made it popular. So people started using it. Okay, so this Wheatstone bridge consists of two known resistors, one unknown resistance, and one variable resistance. Okay, so as I already told you, this R is our I'll take this highlight laser pointer. This R is our unknown resistor, S is our variable resistor, P and Q are the known resistances. And all these four resistances, they are connected in the form of a bridge. Okay, so this bridge is very reliable as it gives accurate measurement of the resistance. If you want to determine unknown resistance, you will definitely get the accurate resistance value. Okay, so this bridge, if you carefully observe, it also consists of a galvanometer. You can see in between this B and D. Okay, here you can see A, B, C, D uh, terminals. Okay, so junctions we can say. So in between B and D, there is G mentioned here. That is nothing but galvanometer. Okay, and it also consists of an electromotive force source, that is DC source, that is E. You can see here E. So it consists of a battery, you can say in other words, battery or a DC source, and a galvanometer. And in between B and D, there is yeah, that is there is a galvanometer here. Okay, and you can see the positive terminal is connected to positive terminal of the source is connected to node A, and negative terminal of source is connected to node C here. Okay, now so as G is connected between B and D, the current that flows through this galvanometer will depend on what is the potential at B and what is the potential at D. Potential means potential difference between B and D. Potential means voltage here. Okay, potential means voltage. So voltage at depending on the voltage at B and D, current will flow through the G. Okay, so I hope you already know that if current has to flow through any element, then current can always flow from higher potential region to lower potential region. Okay, if suppose V1 is one potential and V2 is another potential, V1 is some voltage and V2 is another voltage, and V1 is greater than V2, then current will always flow from V1 to V2. Okay, current can flow from V1 to V2. Okay, so if V1 is equal to V2, if V1 is equal to, sorry, I wanted the eraser, right? V1 is equal to, V1 is equal to V2. Okay, so there is a branch here, and this is V1, this is V2, then current cannot flow through this branch. Okay, the potential difference between, if V1 equal to V2, the potential difference between V1 and V2 will be equal to what? Will be equal to 0. So if the potential difference between any two terminals is 0, then current cannot flow through that branch. So similarly, how much current is flowing through this G? Okay, where is my cursor? Yeah. How much current is flowing through this G will depend on what is the potential difference between B and D. If there is no potential difference between B and D, current cannot flow through this galvanometer. Okay. So this Wheatstone bridge, it works on the principle of null deflection. That is, the ratio of their resistances are equal. Okay, the ratio of the resistance of these Wheatstone bridge are equal, and no current flows through the circuit. Okay, so if the ratio of the resistances of this bridge circuit are equal, then no current will flow through this circuit. Circuit means the galvanometer. So under normal condition, bridge is in the unbalanced condition. So under normal operating condition, bridge will be unbalanced. Okay. So when bridge is unbalanced, current will definitely flow through this galvanometer. So under unbalanced condition, what will happen? Current will flow through this galvanometer. Okay. So if current is not flowing through the galvanometer, okay, if no current flows through the galvanometer, if G is equal to 0, okay, G equal to 0 means current flowing through the galvanometer is 0. G 0 means nothing but current flowing through the galvanometer. The pointer in this galvanometer will have a dial, as you know. I have already shown in this image. You can see here. This is our galvanometer. This is 0 term. This is 0. So if this galvanometer pointer is at 0, that means it is showing null deflection. So if the galvanometer pointer shows null deflection, then we can say no current is flowing through the galvanometer and the bridge is balanced. Okay, so the bridge is said to be balanced condition when no current flows through the galvanometer. Okay, so this can be achieved by adjusting the unknown resistance and variable resistance. Okay, by simply adjusting the unknown resistance and variable resistance, that is unknown, R and S. Okay, P and Q are fixed resistors, we can't vary them, they are known resistances. But simply varying R and S value, we can determine, we can get the balanced condition. Okay, so now let us see the derivation. So I'll give you a minute. If you have not drawn, there is a derivation for this topic. So quickly, if you people draw this diagram and mention in the chat box. Yeah, you just draw the diagram. Draw this Wheatstone bridge. There is a small derivation, which is very simple derivation. We will discuss the derivation and we will conclude this topic within 5 minutes. Okay, climate is not good. I will conclude as quickly as possible. Just draw the diagram. If you have already drawn, just mention it in the chat box. Quickly draw it so that within 5 minutes I will conclude this topic. You have drawn, mentioned, completed. Okay then. Okay. So see here, there is a source here, DC source. The current will start to flow from positive terminal to this junction A. So at junction A, what is happening? Current is dividing into two parts. Current is dividing into two parts. One is I1 current, another one is I2 current. So current. So let us assume I current. Let us assume I current enters here. Current entering here is I. So I is dividing into I1 and I2. Okay. So under balanced condition, let us assume that I1 into P is equal to I2 into R under balanced condition. Okay. So under balanced condition, if you see here I have mentioned the condition exists when current through the galvanometer is 0. So when current through the galvanometer is 0, let us assume current through the galvanometer is 0. Therefore, I1P is equal to I2R. Consider it as equation number 1. Okay, write it down quickly. No need to write theory. No need to write theory. Simply write the equation. Okay. I1P is equal to I2R. Consider it as equation 1. I'm changing the slide. Don't write theory because climate is not cooperating. So I want to conclude quickly. So under balanced when the bridge is balanced, okay. So when bridge is balanced, then when the bridge is balanced, then I1 will be equal to I3 and I2 will be equal to I4. So what is I1? E by P plus Q. And what is I2? E by R plus I2 is E by R plus S. Okay. So okay. So why? Because here this is our source. This is our source E. Okay. No current is flowing through the galvanometer. No current is flowing through the galvanometer. So what will happen? Uh, R will become in series. R will be in series with what is it? Yes, and P will be in series with my cursor is very sensitive. That's why I'm unable to. This is R. This is S. This is P, and this is Q. I didn't draw G here because no current is flowing through the G. So P will be in series with Q. R will be in series with S. That's why E by R plus S, E by P plus Q. Okay. So I hope you know current division rule. That's it. Nothing else. Here I have implemented current division rule. So I1 will be equal to I3 under balanced condition. I2 will be equal to I4, and that will be equal to E by I1 will be equal to I3. That is equal to E by P plus Q. I2 will be equal to I4. That is equal to E by R plus S. Okay. So what is E? E is the EMF of the battery. Now, so now let us substitute this I1 and I2 equation. I1 and I2 equations that you have got here in your equation number 1. Okay, substitute I1 and I2 in equation number 1. Did you complete? Write it down quickly. Completed? Okay. Okay. So I hope you have written these three equations. Let us proceed. I want to conclude. So if you substitute it in equation number 1, you will get P into E by P plus Q equal to R into E by R plus S. Okay. Now here you can cancel E. What is left over? P by P plus Q equal to R by R plus S. And you just cross multiply, you will get P into R plus S equal to R into P plus Q. Just multiply this P with this term and R with this term. You will get PR plus PS is equal to PR plus QR. Okay. And if you observe carefully, here similar terms are there. PR, you just cancel PR. You will get PS is equal to QR. That is our equation number 2. So what is R? What is R? R equal to P by Q into S. Okay. So what is R? R is our unknown resistance. Okay. R is the unknown resistance. So here equation number 2. Equation number 2, it shows us the balanced condition of the bridge, whereas this equation number 3, it can be used to determine the unknown resistance R value. Okay, to determine the unknown resistance R value, I want to erase these. We can use equation number 3. If you have completed, mention C so that I will go to the next slide and I will conclude. Completed? Mention in the chat box if you have completed. Okay, very good. So, okay. So here, what is R? Unknown resistance. What is S? Standard arm of the bridge. Okay. So that is variable resistance. P and Q are the ratio arm of the bridge. That is the known resistances. Okay. So applications of this Wheatstone bridges. Wheatstone bridge is used to for the precise measurement of low resistances. So if we can use this Wheatstone bridge along with the operational amplifier to measure physical parameters such as temperature, strain, or light, or some quantities such as impedance, inductance, and capacitance can be measured using variations on the Wheatstone bridge. So, with some variations in the Wheatstone bridge, we can even measure the impedance value, inductance value, and capacitance value. Okay, so I hope you have understood. So, if you want to draw the diagrams later after this class, um, you can draw the diagrams in your notes by watching this video. Okay, if you have any doubts, you can mention in the chat box. Okay, okay then. Thank you for watching this session. So if I'm going to take online class tomorrow, I will inform you.